As the talks progress in the morning, more and more people start showing up, and as they wake up. We were all up pretty late last night, which might be relevant to this topic of this talk: brain chemistry, how psychoactive chemicals hack the central nervous system. I don't know. Maybe it's all theoretical. None of us have experimented with psychoactive substances, but. Jennifer here is a passion of hers because she's been studying pharmacology for about a half dozen years. She'll soon be a pharmacist. So she really knows her material. And I imagine some of us have some personal experience in this area as well, but the hows and the whys could be particularly interesting. So I just want to welcome Jennifer to Hope, and looking forward to this talk. Thanks.
Hello, thank you. As he said, I'm Jennifer. Welcome to Brain Chemistry. I just finished my Doctor of Pharmacy degree, so I'm happy about that. And, well, thank you. It was a lot of work. I'm going to focus on how stuff works. Over there is my cold virus friend, because I spoke at the last Hope, and he's watching to make sure I do a good job. So I'm going to start with something that amused me that I saw in a toxicology rotation. This is some scratch remover, which is DEA compliant. It's strictly not for human consumption. It's legal in all states. It does not contain LSD, cocaine, MDMA, amphetamine, any of that stuff. It's on a site called Buzz Wholesale. I'm sure this is in no way any sort of, front or psychoactive substance of any kind. So how are drugs like hacking? Well, we have an existing biochemical network with our, brains and nervous system, and cells communicate chemically. So drugs, being chemicals, can hijack various cellular communications and other processes. Some of the ways they can do that is by binding to receptors. Receptors are sort of like, functions in programming. Basically, a cell will have receptors on the outside of its membrane, and chemicals can bind to that. And then on the inside of the cell, stuff happens, depending on the cell and depending which receptor, all that stuff. So there are agonists, which activate receptors, antagonists, which block receptors. Other things drugs can do is change chemical transport, chemical synthesis, the metabolism of things, the release of neurotransmitters and such, gene expression, and anything else that's biochemical. So I just wanted to define, I'm going to focus on the central nervous system, the CNS. This is the brain and spinal cord. It's in red here, and that's opposed to the peripheral nervous system, which is in blue, and that's everything else. Let's see. So the first thing is your brain is firewalled. Basically, it's very selective about what can get in. The transfer of stuff from the blood to cells is selective, and the transfer of stuff from the blood to the brain is particularly selective because your brain and spinal cord are very important. So in this diagram, we have a capillary in red, and then the brain cells attached to it are in blue. And the endothelial cells are the ones surrounding the blood vessel, and they create a barrier. Everything has to go through them to get into the brain. So in this diagram on the top, that's where the blood is. On the bottom is the brain cells, and here are the endothelial cells, just showing some different ways that stuff can get through. on the left, stuff really, water soluble, small stuff. Some things can get through tight junctions that bind the cells together. There's also some stuff can go all the way through the cell. And on the right, C, D, and E are just various ways that stuff can be transported through the cell. Most of the drugs we're talking about would fall under category B or not fall under it if it doesn't get into the CNS. Generally, they have to be small, fat-soluble, non-polar. In my last talk, I actually did a demonstration that I decided not to do this year, having to do with acids and bases and solubility. It kind of ended up like vinegar and baking soda because and exploded, which was fun but messy. But basically, using acids and bases, you can change the solubility of some molecules, which is useful because this can affect whether it crosses the blood-brain barrier or not. Aspirin is an acid, which does cross, but in cases of overdose, it's useful to raise the pH of the blood and make it more basic, because that makes it more water-soluble and it doesn't cross as easily that way, and it's also excreted more easily. To be psychoactive, a drug has to get into the central nervous system, has to get to the brain to affect the brain. So that's why this is important. We've used that to our advantage in developing drugs. On the left, these diagrams, just to mention in case you haven't seen them before, the lines are bonds between carbons, and then N's are nitrogens, O's are oxygens, and Cl is chlorine. So the one on the left is mostly carbons bonded to each other. It's very fat soluble, goes into the central nervous system. It has its antihistamine effects both in and outside of the central nervous system. And one of those effects is to make you very drowsy, just like Benadryl or NyQuil. Those also have antihistamines that are like this. And that's an effect that is on the brain. On the right, we have Claritin, loratadine, which is made more polar by the nitrogens, the oxygens, and the chlorines. They draw electrons to themselves, so it changes the distribution of charges on the molecule. And so it doesn't really cross the brain barrier much. So it doesn't make people drowsy like the old ones do. Very useful. So a friend told me a while back when I was talking about ethanol that she thought ethanol and the GABA agonists would make a good band name. I don't know, it kind of has a nice ring to it. I'm going to talk about a neurotransmitter called GABA, but first we have to understand action potentials. So we've all seen illustrations like the one on the left. I know you have because I used the same one earlier in this presentation. And it's all flashy. It shows the electrical signals moving through a neuron. And on the right is a more technical diagram that shows the voltage that goes through the cell when it fires. The firing is an action potential, and it either happens or it doesn't. But how does this happen chemically? The answer is through magnetism with ions. The main ones involved are sodium, which is positively charged, potassium, and chloride, which is negative. And they generally can't cross the cell membrane unless you have channels they can go through. So on the bottom, I just have an illustration. There are pumps on the nerve cells that basically keep potassium on the inside and sodium on the outside. the cell in general is also maintained at a resting voltage of about negative 70 millivolts. So it's got the potassium inside, the sodium outside, and it's at a negative charge. Stimulus changes that and can make it more positive, but the stimulus has to be strong enough to get it to about negative 55 millivolts. And then at that point, there are channels, sodium channels, which are sensitive to voltage. So those open up. When it reaches 55, there's a cascade, and all those sodium channels respond, and they open up, and sodium rushes into the cell. Now, so we got all these positive charges coming into the cell. The cell then becomes positive. At that point, then the sodium channels start to close and potassium channels open. So you get up to, that peak there, and then potassium starts leaving the cell as the channels open, and so then the voltage goes back down. So then it actually overshoots a little bit, goes more negative, and then you've got, sodium on the inside, potassium on the outside, and those pumps start resetting things by exchanging those two.
It sounds like a chemical transistor.
A chemical transistor? Yeah, I guess I'm actually not as familiar with electronics. Yeah, it makes sense. I think it's a good, it's an interesting mechanism. I find it interesting anyway, which is why I'm talking about it. One would hope I find it interesting. So back to GABA and how this works. GABA inhibits action potentials, so it has all sorts of depressant effects. The drowsiness, relaxation, anti-anxiety effects, and GABA agonists. Ethanol. So ethanol has other actions besides GABA, but that's one of its big ones. So that causes sedation. Benzos like Valium, Xanax, hypnotics like Ambien, barbiturates, propofol, they have effect on GABA, and it slows things down, makes nerves less likely to fire. So the GABA A receptor is a chloride channel. So what happens, how this works chemically, is that GABA or other things that bind to it open up the channel and let chloride into the cell. So that makes it more negative. It might, be negative 70 millivolts, and then, with more chloride, it could go to negative 100 or whatever. So it's going to be harder to make that action potential happen. And I do have a experimental demonstration here. One that is less messy than. Is it? Huh? Oh, okay. Oh, okay. So I don't know, when I was a kid, I loved setting up dominoes. Action potentials are kind of like that because they either go or don't. And you push a domino over, if you push it to a certain, part, it falls over. If you don't, it doesn't fall over. So I've got weights on the backs of these. So obviously there's a certain point where I'd push this over and it would knock all these over. But if I add weight to the back of this, it's much harder to push over. So it takes more, I have to move it more distance before it'll actually fall over. So the action potential, well, the effect of GABA is sort of like that, and just for fun. That was less messy than my volcano thing. Anyway, so there's another neurotransmitter called glutamate that sort of works the opposite of GABA, which applies to this case. There's another thing I learned a lot about on toxicology rotation. There are K2 spice or product names for a pseudo-legal cannabinoid, and they're basically synthetic. They bind to the same receptors as marijuana, and they're basically, the product is basically plant material sprayed down with these chemicals. They were invented for research and then modified by chemists to skirt the law. The Poison Center has gotten a lot of calls about these recently. On rotation, we'd see people come into the ER with seizures. We don't really, I'm sure there's a lot of people who have smoked this and not gotten seizures, but compared to marijuana, we don't really see people come in with seizures with marijuana, but with this stuff, it's been a regular occurrence. So there's some question as to why this stuff causes seizures. And I researched that a little bit. It turns out THC has anticonvulsant activity. Its effect on the cannabinoid receptor inhibits both GABA and glutamate. So inhibiting GABA makes you more likely to seize, and inhibiting glutamate makes you less likely to seize. But it's thought to have a stronger effect on the glutamate. The synthetic cannabinoids, though, a lot of them are more potent, sometimes 4 to 5 times more potent. So perhaps they have a stronger effect on GABA. So to talk a little bit about pain, because people always find painkillers interesting. Some of the common mechanisms, like I've been asked before, how there are certainly painkillers that just numb you, like when you go to the dentist and you get lidocaine, it just makes you numb. And clearly there are some others that don't numb you. Some of those are anti-inflammatories, so they inhibit prostaglandins, which cause pain and sensitize your nerves when you have tissue damage, when you're sore. But if someone were to stab you or something when you've taken an anti-inflammatory, it's probably not going to make much difference because that's a acute pain. But then there are centrally acting ones as well. And the CNS actually has pathways obviously going from the body to your brain, which transmits the pain signal, and then it has descending pathways that go from your brain down to your body, and they have the ability to inhibit pain signals. So just some basic, some of the centrally acting ones. Opioids, they bind to opioid receptors, and pretty much they ultimately have an effect on glutamate in the spinal cord. So they inhibit it, and again, the nerves are less likely to fire there. There's also a couple unique substances that are opioids, but also affect serotonin and or norepinephrine. Those neurotransmitters also seem to have an effect on pain. The cannabinoids, also, those are still being investigated. It's not real clear what the mechanism is. Neuropathic pain is pain from nerve damage, so the opioids are less effective, but stuff that affects serotonin and norepinephrine is often helpful for that. And then there's acetaminophen, which is kind of its own thing. It's an anti-inflammatory, but in the central nervous system instead of outside of it, like ibuprofen. again, using the blood-brain barrier to our advantage, opioids have, well, there are opiate receptors in the gut. So opioids slow down your gut and they can cause constipation. Of course, constipation would be a great side effect to have if you had diarrhea. And there is over-the-counter Imodium, loperamide, which is treatment for diarrhea. It binds to the opioid receptors, but it doesn't really get into the central nervous system. So it has that peripheral effect, but doesn't have the opioid effect that others do. So it doesn't kill pain or, get you high or anything. It actually, some of it actually does cross the blood-brain barrier, but it's pumped back out by P-glycoprotein. So it's sort of like if you have a boat that's leaking a little bit and you have buckets, you can get the water out, unless it's coming in just, too fast. But generally it stays out of the CNS. There are some chemicals out there that inhibit P-glycoprotein, such as quinidine, and so that allows some loperamide to stay in the CNS and have CNS effects, which are like opioids. Another interesting toxicology case, I probably get way too excited about these things, but there was a lady who came in and she had OD'd on loperamide. She took about 200 of them over like the past couple days. Yeah. Well, the immediate concern usually with, I guess she was trying to detox herself from, from other opiates using loperamide. It's not unheard of apparently, but the usual concern for toxicologists with overdoses and opioids is respiratory depression. Your breathing slows down, and if that happens for too long, you can have organ damage and brain damage and eventually die. But with her, there was a much more pressing problem of her heart going into this arrhythmia called torsades, twisting of the points, and it looks like a party streamer on the ECG. And that could be an effect from quinidine, although she tested negative for quinidine. They actually had to shock her 15 times because she kept going into this rhythm. It was interesting because, we don't know what caused it. It could have been the loperamide itself because we really don't know. We don't do tests of, 200 loperamides on human subjects, So, moving on to monoamines, norepinephrine, dopamine, and serotonin. A lot of psychoactive drugs have a phenylethylamine structure. This is, the phenyl ring. Ethyl is the 2 carbons, and amine is the nitrogen. And our neurotransmitters, norepinephrine and dopamine, have this structure. So here you can see some patterns with some various psychoactive substances, including, some that are prescription and some that are illegal. They all have this phenylethylamine structure, which gives them some activity that has to do with, neurotransmission. So back in the 50s, I believe, it was noticed that that monoamine oxidase inhibitors, they basically inhibit the metabolism of monoamines, the serotonin, dopamine, norepinephrine. So that leads to more of those neurotransmitters in your brain. And that led to, they noticed that these helped people who were clinically depressed, which led to the monoamine hypothesis, which is that When you're depressed, you have low levels of monoamines, and all the antidepressants that have been developed, affect these monoamines, and they increase the amount of it in the synapse. The thing is that the increase happens pretty quickly. You take a Prozac or something, and it absorbs into your bloodstream, and it gets into your brain, and that same day it starts to affect the serotonin. It inhibits the reuptake, so there's more in the synapse. But it takes weeks to get the antidepressant effect, like the long-term effect against clinical depression. In the past couple decades, there has been a new hypothesis that's been gaining momentum, which is that it's really involving neurogenesis, the growth of new neurons in the hippocampus. This is a normal process, but there's evidence that people who are depressed or have long-term anxiety or bipolar have diminished neurogenesis. And it's discovered that antidepressants ultimately result in more neuron growth in depressed patients. So there's evidence that this is why they work, and that this is an effect that's downstream of the effect on monoamines. Other things that help depression, therapy and exercise, they also have a biochemical effect on our nervous system and our brains. And so they can also increase neurogenesis. So this is still being investigated more, but it's very interesting to me. Another instance of using the blood-brain barrier with monoamines, Parkinson's, we can treat with dopamine, and dopamine doesn't cross, so we have to use L-DOPA, which is a precursor. The precursor gets metabolized in the body to dopamine. The thing is that dopamine has a lot of side effects. It has some, in the brain, we can't really help that, and it has some side effects on the heart, on blood pressure, stuff that's outside of the central nervous system. So what we do is there's a chemical called carbidopa, which blocks the metabolism of L-DOPA to dopamine. And carbidopa does not get into the central nervous system. So it blocks the metabolism. Essentially, it prevents the dopamine from being created in the peripheral nervous system and restricts it to just the central nervous system. So that greatly helps with all the side effects that are on the outside. So we always use the combination. Serotonin. Serotonin, to me, it's an old neurotransmitter. I think of it like as sort of the JavaScript of the nervous system. It's everywhere. It's ubiquitous. It does all kinds of things. There's 14 different receptor types that we know of. Most of it's not in the central nervous system. Most of it's outside, does other stuff, but of course I'm focusing on the central nervous system. And it has these are the pathways. It has effects on mood and memory and perception and fear and all kinds of stuff. So it's everywhere. It's a really complicated neurotransmitter. And some of these structures with serotonin and some of the similarities of psychoactive substances that in some way affect serotonin. I have some hallucinogenic, psilocin, DMT, LSD. Sumatriptan is a drug that's used to treat migraine headaches. With the LSD here, it's a little harder to see the structural similarity, so I highlighted it on this slide. On the left, I turned the serotonin molecule there on the bottom to match. LSD and some of the other hallucinogens are 2A agonists. although they're still really not fully understood, unfortunately. There's really a lot of stuff we haven't figured out about the nervous system. Like, I've learned a lot, but I've ended up having more questions than I started with. So I did find some stuff about geometric patterns, like people report actually in migraines and in like hallucinogens, that they see certain types of patterns, among other things. And basically our retina, the nerves from our retina are mapped onto our visual cortex. V1, there's different parts of the visual cortex, but V1 is the primary one. It activates with even if you imagine really vivid imagery. People who have migraines sometimes get a visual aura that involves like lines and geometric things going across their visual field. And it's been determined that migraine, or the precursor to migraine, the aura, involves what's called a cortical spreading depression, which is a electrophysiological event that is a nerve hyperactivity followed by a suppression, and sometimes it will go across the visual cortex and sometimes not. And it's when it goes across the visual cortex that you see all those patterns. So drugs that cause firing in the visual cortex could also produce those kinds of patterns. It hasn't been proven, but there's a paper in 2002 that had a rather elaborate computer model. It was a neural computation magazine, so that was kind of interesting. They talked about some of the different kinds, like spirals and things, and tunnels, and how the visual cortex, like the mapping, is not, like basically the area where you're focused on takes up a lot more space in the visual cortex than your peripheral vision. There's more information here. So that can cause so they did it mathematically and showed that could cause a distortion, so that you would see, a tunnel if you had certain patterns of firing in your neurons. The mathematics were beyond my abilities. I stopped at Calc 2. So this was just an example of an equation here at the bottom. So I don't know, it's a possible mechanism. So in conclusion, I actually finished up a little faster than I thought I would, but that'll just leave more time for questions. Brain chemistry can leave us with more questions than answers. Marijuana is safer than the legal weed. Giant foam dominoes are less messy than acid-base extractions. And DEA compliant scratch remover is available online. So, just some additional resources for you guys. I'd recommend arrowwood.org, has a lot of information about psychoactive substances. Medscape for more medical-oriented stuff. Wikipedia is pretty accurate usually. I've gone on there and edited some articles and verified. You always want to double check the sources, but it's actually pretty good. And then if you want to email me with questions or corrections, PayPal donations, job offers, that's all fine. I hate doing bibliographies, so I didn't do one, but if you want my references for this presentation, I have them, and if someone really wants it, I can format that and give you my citations. So that's about it. Questions?
Hello, hello. Yeah, I have a question. I love you.
Do we have any mechanism for objectively, for a doctor, detecting when a patient is experiencing pain? So far as I know, it's mostly subjective. I go to the doctor, I say I have a headache. The doctor doesn't know how much of a headache, what kind of headache, anything. It's just what I tell the doctor.
Yeah, that is pretty much the state of pain management right now. It is very desirable and discussed in research to find a way to somehow measure, someone's pain. But right now, it's all like, they'll ask you how much pain on a scale of 1 to 10. It's basically based, what you say. Everyone's experience of pain is different and their tolerance is different. So we're really, it's frustrating, but it is a limitation right now.
We'll know if you're being a pain in the ass.
Yeah, we'll know if you're being a pain.
Hi, I just heard about the neurogenesis hypothesis that you were talking about, and in the internet culture, there's a drug called paracetam online. Just the smart drug is one of the first drugs of the family for the racetams. I was just wondering if you've heard of this drug and if you have any opinion on how that might help with depression.
I've heard of that one. I would have to look it up because I don't remember all the details. If you can email me,
I will.
yeah, then I'll see what I can find about it.
Hi, thanks for a great talk.
Mhm.
Is there any information on the naturopathic stuff, and does it have similar reactions, like, for depression or pain relief, valerian root, St. John's wort? Is it similar neurogenesis?
Yeah, there is some information. I mean, a lot of the stuff there isn't much information about because it hasn't been studied, and like a lot of the herbals, there'll be some new combination they come out with that's really kind of random. St. John's wort does have evidence. It affects all three of the monoamines I mentioned: norepinephrine, serotonin, and dopamine. It also interacts with 1 billion prescription medications, so if you ever take it, make sure you tell your doctor about that. And yes, it does also fit in with the neurogenesis. Valerian, I am not as familiar with the evidence on that. It's one of the more studied ones, and it seems to have some effect on anxiety and sleep, but I'd have to look up more detail about that.
Well, I was wondering about substances like Valium, for example. You explained how they depress the action potentials and everything. So you would assume that an overdose would eventually lead to, collapse of the actions and death. So first of all, why does an overdose not kill you? And second question would be, why do combinations of these substances, like, for example, Valium combined with a certain malaria drug, become totally fatal all of a sudden?
Yeah, the benzodiazepines, basically they inhibit, but they have a ceiling effect. So all by themselves, an overdose, like at a certain point, they cannot, let more chloride into the cell. But if you combine them with some other sort of depressant, that has another mechanism, more action on GABA, then that could kill you because then at that point it could slow your breathing down enough that, you die.
I was wondering if there's been any serious work on trying to stimulate the brain using just sort of electrical impulses directly rather than using drugs to sort of causes the neurosubstances to fire, just zapping neurons directly or something like that, and how reliable that is and when that would be mainstream.
Yeah, well, one actual electroconvulsive therapy is still used sometimes for very severe depression, and that involves basically shocking the brain cells. It's done with anesthetic, I believe, because basically they cause a controlled seizure or a controlled convulsion, and that seems to it seems to be very effective for those really deep, dark depressions that are hard for people to get out of, but it has some side effects on memory and things. It's not as easy or as inexpensive as taking medications, but it is out there, and it is an effective and official treatment option.
Okay. Just one other question. Just do you know anything about how like motion sickness drugs like Dramamine or similar things work?
Yeah, a little bit. Let me try to remember exactly. Yeah, diphenhydramate, meclizine. They have both antihistamine and anticholinergic effects in the central nervous system. I'm not sure exactly their effect. I know we have a chemoreceptor zone in our brains that when it's stimulated, which opiates, for example, tend to stimulate that. It makes you nauseous. Probably protects you from getting poisoned if you were, when we evolved, if you ate something random and then, it had that effect, it might cause you to puke. But I'm not recalling exactly the mechanism. All I know they're anticholinergic and antihistamine.
Okay, thank you.
Hi, and thanks for a great talk again. Can you talk about why stimulants make you focus instead of more scatterbrained? Certain stimulants.
Yeah, well, you have something like amphetamine salts, Adderall, or Ritalin, and I mean, in general, I think they release norepinephrine and dopamine, and that activates your sympathetic nervous system. So you've got some mental effects and some peripheral effects, and it's activating. And the purpose of that is usually it's the fight or flight sort of response. So it helps you focus and get ramped up. In the case of ADHD in particular, it seems that there might be a lack of, there's something going on again with norepinephrine in the brain and dopamine, and that this extra stimulation seems to help. I'm not a neurologist, so it is a little like I wonder about this stuff too, and like every question I have, I investigate. I find out like, oh, they release norepinephrine, and then okay, what's that do, and what's this do, and I end up with more questions than I started with. But that's what I know about them.
And sort of to tack on just a little bit, and you can totally, because you semi-answered this, but if you do any kind of like brain training, is there a noticeable change in the chemical effects of your day-to-day neural activity?
Well, I don't know the research that would have to do with that, but in my personal opinion, based on what I know about biochemistry, it's plausible to me. I would think that there would probably be methods of brain training that are more effective than others. In the case of ADHD specifically, it doesn't seem that there's ever enough to fully help someone who's really struggling with it. But it could have some effects, I think.
Cool. Thanks.
Thanks for a great talk, by the way.
Thank you.
I understand we build up tolerances to certain drugs. I was wondering if there were any sort of complementary drugs that will reset those tolerances, maybe particularly for stimulants, for example.
Well, the short answer is not that I know of. It could, probably not at the moment. It's something I could look at, if you email me, and I could look just to see. you know, I don't think there's anything out there that we know of right now. That doesn't mean they don't exist, possibly, but we just don't know of any.
Thanks.
There's some research into preventing tolerance with NMDA partial antagonists. That's how magnesium or other
NMDA partial antagonists, there's research into
not reversing tolerance, but
preventing tolerance. Okay, that's something I might look up later because it's interesting.
Hi, I'm wondering how anxiety disorders work in the brain chemically and how anti-anxiety meds differ from differ from other types of meds.
Well, there is a lot of crossover with anxiety and depression. Yeah, I mean, first-line treatment with anxiety disorders is usually a SSRI, a serotonin reuptake inhibitor, which are also antidepressants. The benzodiazepines are also used in anxiety because they have a pretty profound and direct effect by being very sedative. But they're not so much, long-term, because tolerance can build to those, and the SSRIs work better. There's another drug called buspirone, which is in a class by itself, I guess. It's not an antidepressant, but it does have an effect on serotonin and seems to work long-term. It takes a few weeks to work for anxiety. So I don't know, does that answer your question?
I guess I'm sort of wondering, if we're using the same drugs to treat them, what chemically is the difference and similarity between anxiety and depression? Like, are they very similar chemical phenomenon?
I think that is still somewhat of a mystery. I mean, depression itself, like as much as we have learned about the biochemistry of it, some of our basic questions, like, why do we even, why do we have a large number of people who have, gotten clinically depressed and, when anxiety and stuff seems to be so unhelpful, or having an anxiety disorder. I don't think we really know. It's complicated, and again, it's one of those things where we understand a lot and yet very little.
Thanks.
So this is a politics question. I'm curious about how, if at all, legitimate research can be done these days on Schedule I drugs, and how that works in the research community. Is it a brick wall? Is there a way forward for researchers to do legitimate work on those kinds of things?
There is a way forward. I don't know a lot about the politics, but you might want to look up MAPS. There's an organization called MAPS that is, I forget what it stands for. Something. Huh? Oh, Schedule I, yeah. So in our country, the drugs are controlled, well, some drugs are controlled substances, and they put them in these schedules. So Schedule I is basically totally illegal. Schedule II is, it has a really high potential for abuse and harm, but it still has legitimate medical use, such as morphine or amphetamine. Those are Schedule II because they still have a legitimate and accepted medical use. But Schedule I would be, stuff like LSD or marijuana, heroin. Yep. So the stuff you really consider,
really fun stuff.
Illegal drugs, right? So it's difficult, ecstasy. It's difficult to do research on them, that's for sure. Some of the research has taken place in other countries. As far as I can tell, it's probably pretty difficult over there too. I'm not sure exactly how much of a brick wall, so that's something where you might want to find the MAPS website. And also then you can see some of the research that's been done on LSD and MDMA for, you know, psychiatric things and stuff like that.
Thank you.
First, I just want to say thank you. And my question has to do with long-term supplementation of really common drugs like caffeine or nicotine. People have been taking these drugs for hundreds of years daily, and they do it because it makes them more alert or whatever. Now people are experimenting with more types of supplementing or controlling what they're doing to maximize the benefits they get from them. And I was wondering if you had a position on something like that. Do you drink coffee, or do you choose not to because of some reasons, or what are some cool things that are coming out that people are taking for whatever benefit?
Yeah. Well, I mean, caffeine, I don't really avoid it or use it much because it doesn't, you know, do much for me. A lot of people who have like mild ADHD seem to benefit a lot from it because they self-treat. And other people just like coffee and drink a lot of it. As far as I know, I mean, there has been research done on caffeine, and I haven't seen anything that says it's, you know, particularly dangerous or beneficial. I mean, you know, I wouldn't recommend drinking 20 cups of coffee a day or anything. Yeah, so I don't know, I can't, you know, I don't have any opinion on that. Other supplementation, I guess, like I tend to be skeptical about the benefits of you know, a lot of, you know, vitamin supplements and herbal supplements that come out, because a lot of it's just pure hype. You know, nicotine, you know, obviously smoking is harmful to your lungs, and nicotine itself is addictive, so wouldn't recommend that, but we kind of know, you know, you can find out about the dangers of that.
However, in the right conditions, small amounts of nicotine will actually put your brain in a position where you'll actually be more sensitive to stimuli around you, which can be very useful for on a battlefield, among other places. Assuming you're not addicted to it. If you are, it does not do this. So it has its uses too.
He says it can put you, that nicotine can put you in a more alert state that would be useful on a battlefield. I mean, nicotine could be, like, has some stimulating and relaxing effects. It's not that, you know, a dose of nicotine is, you know, bad for you. It's just that it's, yeah, it's just that it's addictive and you build some tolerance and everything, so.
Well, but Adderall is addictive and people are prescribed that every day.
Yeah, Adderall, yeah, it is addictive, you know, usually to people who like, it's, I gotta wrap it up, so I'll make this my last answer here. Adderall, it's considered a dangerous substance, that's why it's Schedule II, but it's, obviously it's a real medical benefit for some people, and in the context of a medical, you know, a relationship with a physician, you can monitor for all the negative side effects that it has and adjust dosages and make sure you can really maximize the therapy so you get the most out of it with the least side effects. So thank you all for coming, and email me if you want to.